Practical laws in transformers. So remember, until now, the equation that we have is for transformers that are ideal, perfect, no power loss. However power you give in the primary side is however much power you have on the secondary side. There are, however, many reasons why it should be lost. Okay? Right, all you have to do is you go back, right? You take your laptop adapter. Inside your adapter has the transformers. You just touch it. Is it hot? Right? It's relatively hot compared to your own body temperature. Hence, there is temperature loss. Okay? Efficiency. This is a concept that is taught to you by your work energy power lecturer, which is me. Well, anyway, for transformers, there are a few ways in which you can lose heat. Right? First, there's resistive heating in the coils. That means the coil itself, the wires have resistance. Right? That was one of the assumptions that we said that we had to make before we had the equation of turns ratio equals to Vs over Vp. Next, there's heating due to eddy currents. I'll explain that a little bit more. There's heating due to hysteresis. If you don't know what that is, I'll tell you. There's also leakage of magnetic flux. So 1 and 4, right? 1 and 4 is clear. It's easier to understand, right? Resistance in the wires, leakage of magnetic flux. Okay, so number 1, not going to bore you. This is what the heat loss will be. Okay. So if you have a non-ideal transformer, can you use the equation that we gave you? The answer is no. Right. Number 1, not a problem. What is eddy currents? How many of you know what are eddy currents? How many of you don't know? Right. Eddy current. Do you learn it in EMI? Those who know, did you learn it from EMI? Electromagnetic induction, the previous lecture. No? Yes? Okay, let me try to explain what it is. So follow me, try to follow me. In your electromagnetic induction, in your electromagnetism, look at this coil. The current is coming in. Right, maybe let me draw in a red pen so that the viewers at home can see it. Current is coming in, turning around this coil. Right, so if you use your right hand grip rule, what is the direction of B field induced by this current? Going up. Right hand grip rule, grip. Your fingers are the current. You have B field pointing up. Easy. Now, what happens is this, the iron core or the iron metal thing you wrap around, it senses this change in magnetic field. Right? So until now it's electromagnetism. The next step will be electromagnetic induction, that chapter. It senses this change in B field. Does it like it? No, it does not. Well, actually it has no feelings, but let's put it that way. It does not like it. So what happens? It tries to resist change. It tries to resist it. So it wants to create some B field to counter that. Right? That is basically your Faraday's law and your Lenz's law combined together. Okay? So it senses a change. It tries to create a current to counter that. Tries to create a current that will generate a B field to counter that. So it wants to create a B field pointing down. So using a right-hand grip rule, what is the direction of current that you see? Right? It is this direction. It is here, right here. This is the direction of current that you have. Okay? So if you have that EMF, right, because the rate of change of flux is fixed, you have the EMF, you have a very big piece of metal for the current to flow through. Is the resistance very, very low? Yes, the resistance will be very, very low. Right? Which means the current will be very, very high, which means P equals I squared R. The power loss due to eddy current heating will be very high. Okay? You get me? Right? So we want to prevent that. We want to prevent that from happening. What did the scientists, what did the smart scientists before us and engineers, what did they do? they sliced up the iron core. Right? Remember the criteria, the V, the EMF part you cannot change, but you can change the R part. By slicing it up, right? Previously, the current you saw went like that, one big loop. Now, right, it's sliced up. There's a line in between them. Right, I mean, you are looking from the top like this. The current looks like this. Right, it's small and tiny. There's a small place to go. The resistance is huge. The current is small. So using P equals I squared R, the power loss becomes a lot smaller. All right, so these are laminated sheets which are not conducting. Okay, Ken? Ken, huh? Right? I can draw a not so small one so you can see the direction of current. Like that. Done. So this is eddy currents, right? And we have a way to limit it. The next one, however, we have even less ways of limiting it. That means all transformers in reality are not ideal. Next one is called hysteresis. Not hysteria or hysterical or what. Okay, it's hysteresis. What is hysteresis? Is this. Right, your iron core will have a certain magnetic direction, certain magnetic pole. The magnetic pole is the orientation of the atom and the electron itself. Right, it's a magnetic orientation. Now, when you flip it, that atom and the electron, that arrangement have to turn. It has to turn. Okay? So if you keep turning it, it keeps turning around. You keep changing the magnetic flux. It keeps turning around. It has to turn. It has friction. Okay. Hence, there's heat loss. So one way to think about this is this. Imagine in the morning when you are taking the MRT, it's packed. Everyone faces the same way, right? Now then you have one person who is standing at MRT and is turning like that. Okay? Now he's going to rub shoulders literally with the person to the next and to the right, to the left, to the right. That's going to generate friction. Now imagine the whole train is packed and doing this turning. First, when you step into the train, I think you shouldn't go in because it's weird. But the point is this. The point is if that is what you, that generates a lot of heat, right? The whole movement like that, and that's what you're actually doing to the iron core. Where the iron core is turning, to turn it requires energy, but as it's rubbing each other, it loses heat, right? Oh. Right, hysteresis explained. Good. Next one, flux leakage. Remember, we always draw the diagrams like this. Oops. We always draw the diagrams like this. Right? At the very start, I said, look, the diagrams is what we draw. But in reality, we always connect it like this, patented in 1886. Oh, wow. Patented 1886, I don't know how much older than you. Much older than me also. Why? Why do they do that? Why do they put the coils like that? It's because if you connect on opposite ends, there's a chance for the flux to escape. Right? The flux that you generate can escape. But if you put it like that, the chances are that you will capture as much of the flux. The red one will capture as much of the flux as generated by the coil on the inside. You overlap the coils completely, you will capture most of the flux. This is a very smart concept. Okay? So here they also show you that what you see in the circuit diagram is not the same as what is in reality. Alright? Right. That's that. Done. Next, we can move on to the last part of our lectures, right, which is using a single diode to explain half-wave rectification. So at the very start of the lecture, series, I've told you that it is important to use AC. But when you charge your phone runs on DC, right? Your phone runs on DC. So how do you then, I mean, you can't literally charge your phone with an AC. Your phone will not charge properly. Half of the time it's charging, half of the time it will be discharging. So you must convert your AC to a DC. So how do you do that? Right? You use a diode. You have learned this in the DC circuits, but let me just stress this if you don't know. The diode looks like this in the circuit diagram, right? It looks, and there's an easy way to remember how you let the direction of current flow. You have a play button, correct? This looks like a play button. The play button, it goes in the direction of the arrow. Literally, when they designed this, I think this was a concept. Okay? You all know what a play button, right? Because you don't have cassette players anymore. But you all know what is a play button? Where do you all learn that play button from? Videos. All right, that's right. You all have videos now, that's right. Right, I learned the play button from a cassette player, right? So, anyway. Sorry, age gap. Next, when you have it in the correct direction, it's called forward bias. The current will flow. When you are having your battery and the diode opposite direction, it's called reverse bias, no currents will flow. Okay, Ken? These are the simple stuff. So moving on, we have this. Let me explain this page carefully. Look at the circuit. This is the applied voltage. This is the applied voltage. If you put a voltmeter across it, this is what you will measure. Oops. This is what you will measure. You will measure this graph that you have over here. Up, down, up, down, up, down. Okay? But if you have a diode applied here and you put a voltmeter here, this voltmeter that you will apply, in this case they put a current here. You put a ammeter, you will measure this current. If you put a voltmeter, you'll see a voltage graph that also looks like this shape. Okay, it looks like this shape that you see below. Okay. Right. Clear enough? Because only the positive side allows it to go through. When it's going the other way, it's completely blocked. Any questions? Any questions at this point? No, very good. Thanks for shaking your head. Thank you. Lets me know that you know. Okay. So that's how that what you have and what you get at the end. Very good. Moving on. The IV characteristic of a PN junction, I learned from my students in class that you will introduce this in your DC circuits or COE, one of them. However, I think this part wasn't mentioned, the breakdown voltage part wasn't mentioned, so let me mention it to you. Right? You need to know that the diode, if you keep putting it in the reverse bias, at a big enough reverse bias, it will actually break down. At a big enough reverse bias, it will actually break down. So that's something to take note of. You have a breakdown voltage, okay, which goes almost vertically. Okay. Right. Now that you know what a diode is and how it works and affects a circuit, you see that how it can rectify the circuit, right? From AC, you get a DC because the current only flows in one direction. All right. So example 11, they give you this, they gave you the equation, R equals to 9.0 sine omega t. They give you the resistor, right? And they ask you to find the root mean square current and then the average power. All right, this is a typical question. How would you do it? Right, so note that in a normal question, the graph actually wouldn't be given. You have to draw it yourself. Okay. So, assuming this is a usual question, you actually draw this graph yourself. And you have to find the root mean square. So to root mean square, what must you do first? You must square it. And remember, A sine graph when it reaches 0 is pointy. A sine square graph when it reaches 0 is curvy. Right? Do not draw pointy ends. I like curvy ends for a sine square graph. Don't interpret wrong. Now, you square it, you will get this kind of graph, right? Maximum 9 becomes 81. I becomes I square. A becomes A square. Root mean square. You square already, you must mean it. Now, when you mean this, you realize there's some difficulty, right? Because you have a sine square in the first part, then suddenly there's nothing. So let's break it down into two parts, right? That's a strategy. The first part, if you mean it, is actually 40.5. The second part, if you mean, is actually 0. So if I give you 40 apples on the first section, in the first amount of time, I give you 0 apples in the next amount of time, on average, how many apples do you get over that whole period of time? 20, right? So on average, the mean value will be 20.25 or 20.3. There you go. So this is taking the mean. All right, and once you have mean it, what can you do to it? You must root it. Okay, you root it back. Now, isn't that interesting? The maximum current you have is 9. In the rectified circuit, single diode rectified circuit, the root mean square current is actually 4.5, exactly half. Exactly half. It's not coincidental, it's really like that. You can actually do the math a little bit and see why it's exactly half. Okay, so this is interesting for you to remember. Okay, if you like a quick way to get to the answer, and the answer never asks you to explain clearly, just say state, you can immediately just say 4.5. Right, so this is the first example you see. If you actually know this equation, 11a, you can directly write the answer, provided it's only 1 mark, state the answer. Right, but if it says calculate, then you should show some working, show the methods in which you get to this step. Okay. Next, they ask you to find the average power. Okay, wait, so one more time, square it, mean it, root it. Okay, fine, whatever. Right, find the average power. P equals I square R. You know the power. Done. Right, you know the root mean square current, you know the mean square current, you can find the power. But can I ask you, how does it compare? Two questions are, how does it compare to the maximum power? And how does it compare to the non-rectified power? What do you all get? Is it already up there? Is it right down? Okay, so think about it. How does this power you have compare to the maximum power? Anyone calculated? The maximum current is 9, right? The root mean square current is half of it. So the root mean square, the average power is actually a quarter of the maximum power. Can see or not? Huh? And since your normal sinusoidal power is half the maximum power, this is actually half of your sinusoidal power, so it's a quarter. Okay. Sinusoidal one, the root mean square power, the average power is half of the maximum power. This one is half of that, it must be a quarter. Okay? Right. Ooh. Next example, number 12, is only 1 mark. It's an A-level question. Can you do it? I give you 2 minutes. Go. tomorrow got a lot of people sleeping. Okay, right. Anyone of you found difficulty in doing this question? Right. If you find difficulty, what do? You flip back in the previous example, right, and see how you do it. Or, if not, students always tell me, Mr. Ho, the tutorial always so much more difficult than the lecture. Not true. This tutorial is about the same as the lecture because I gave you so many examples. 12 examples. Oh. So it's actually quite easy. Right? So here you know that half of the time is 170, half of the time is 0. You can just take 170 square divided by 2 and square the whole thing. So here we use 9 to show you that it took 9 seconds. Oh, actually, you don't need to put the 9. It can be just 170 square divided by 2 and square rooted, you get this answer. Okay? Done. Hope most of you got this right. Okay. No, it's not yet the end of the lecture. Why? Because you look at this. Where is it? Okay, here. Look at this. I ask you. If every time you use a single diode to rectify your AC circuit, what happens to the power? You lose how much of your power? You lose half of your power. You spend so much technology to make an AC circuit, to invent a transformer to pump up the voltage so that you lose very little energy. You design your transformer so well, you design your wires, your generator so well. You don't want to spend $10 and only get back $5, right, every time. Correct or not? So what do? This is not strictly in your circuit, but it has appeared, right? You know H1 don't take AC, right? But this diagram came out in a H1 question. Look at how evil it was, or rather in creative table. So I must teach you full wave rectification using 4 diodes. Okay, using 4 diodes. So look, follow me. It's behind, right? If this part is positive, your current will flow here. When it reaches here, it cannot turn left, it has to go to the right. Goes here, and it goes downwards through the resistor. Downwards, remember it's downwards. So the resistor sees the current flowing downwards through it, when the current here is moving upwards. Next, the current comes up, moves to this point. At this point, a lot of students ask me, why Mr. Ho, why does the current not flow to the top again? Why? That's right, because you have already moved through a resistor. You have moved through a resistor, the potential at this point, at the top, must be higher than the potential here. The current only moves to a lower potential. Okay, so it has no choice but to move down, come back, complete the circuit. Okay, so I'll erase all this first. But the point is, the current through the resistor on the output side is downwards. This is the key takeaway. Now you reverse the direction, same thing. Come down, come here. Cannot turn left, go right, come down. Go down again, okay. Very important, it goes down through the resistor. Come left, go up. Oh, can I go up? Yeah, I cannot go down because here is higher potential, so I must go up. Complete the circuit. But you realize in both situations, the current in the resistor is downwards. It's always in the same direction. It's one direction. Right? Hence, you get something like this. Okay? Are you happy? Any questions? No? I have a question for you. Is this good enough? It's not that. Because can you imagine, I'm singing, right? Then my voice goes, I sing one pitch, E, and the sound comes out, E, because your current is up and down, right? You go E, E. Imagine Adele, right, sing a song, very nice, and suddenly at the most impactful point, no sound. Sad, right? We gotta lose it. Sad, okay? Okay, sorry, I can't sing. I stick to my job as a teacher. But I was trying to make a point. So what do you do? What do you do? There's something called a capacitor. Alright? You will learn it actually during your lab. You will learn it. Everyone will do it this term. Alright? What happens is that this will charge will have a current going through the resistor, but at the same time it will charge out the capacitor. So that when it goes down below a certain value, the capacitor will provide that voltage to smooth it out. Okay? So this is a really smart way to change an AC to a DC. Okay? Right. That's it for my lecture. Wait. But I promise you, the teachers, that I will do tutorial with you, right? Because we will finish early. Right? So can you take out your tutorials now? Right, let's go through that.